Okay, let's go ahead and take a look at graphing polynomials. Now, when we go ahead and look at graphing polynomials, the first thing that we're going to look at is the analysis and the relationship between the zeros, real and imaginary, as well as the number of x-intercepts that your graph will have. So let's go ahead and start off first with the degree 1 polynomial, which of course is our linear polynomial. Now, being that we have a degree 1 polynomial, the maximum number of real zeros that you can have is 1. Okay, and so we have a possibility of having one real zero or no real zeros. Now, if we go ahead and take a look at the imaginary zeros, being that we know that they're always going to come in conjugate pairs, and the smallest number besides 0 is going to be 2, then there's no way that a linear function will ever have imaginary zeros, because that way you would actually have more zeros than the degree of your function or your polynomial. Therefore, for both cases of the real zeros, for 1 and 0, the imaginary zeros are 0 and 0 for both of those. Now, if we go ahead and take a look at this particular case here, notice that this is going to have a particular slope and a particular y-intercept. So therefore, it's going to cross the x-axis, which is why we have a real 0, and that's going to be represented by an x-intercept. Now, this particular polynomial, on the other hand, y is equal to a sub 0, where a sub 0 is not equal to 0, is not going to have any real zeros, because this is a horizontal line that is not the x-axis. So we know that there is not going to be any x-intercepts as well. So I think with the degree 1, or linear polynomial, I think that's very familiar to all of us, as is possibly the degree 2, or the quadratic polynomial. Now, we said that in order to determine the real zeros or imaginary zeros, or the types of zeros that we have, we always use the discriminant, which is represented by delta. And the delta is actually going to be found under the radical sign when you actually look at the quadratic formula. So if we go ahead and take a look at when the discriminant is greater than 0, then we're going to have two real roots, and they're going to be conjugates of each other. And being that the maximum number of roots that we can have altogether is 2, then we know that this number of imaginary roots has to be 0. Now, the amount of x-intercepts, of course, is going to be 2. When we had the delta being equal to 0, then that meant that we had 2 repeated real roots, no imaginary roots, and then, of course, 1 x-intercept. And that's when the vertex was actually tangent to the x-intercept. Now, if we had the delta being less than 0, then what we have are no real zeros, and we also have the 2 conjugate imaginary zeros. And because they are imaginary zeros, they don't show up as x-intercepts. Okay, so I'm hoping that the quadratics are also very familiar based upon the value of the discriminant in terms of telling us exactly how many real roots they have, how many imaginary roots they have, and of course the respective x-intercepts for those particular cases. Now, we're going to move into something that's a little bit unfamiliar now. We're going to take a look at the cubic functions, which is a degree 3. So notice that what we can have then is the maximum of 3 real roots. So we know that this is going to be 3 because there's going to be 3 different real roots. And we can go ahead and say that this is what it's going to look like. And then the imaginary roots, of course, are going to be 0 because we've already got exhausted the number of zeros that we have with the real zeros. And all of them are real, so then they're all going to show up as x-intercepts. Now, if we go ahead and take a look at the 3 real zeros with 1 repeated, then of course this is what the function will look like. It's going to have a repeated linear factor and another linear factor. So there's really going to be still 3 real roots with 1 repeated. There are still no imaginary zeros, but in this case there's only going to be 2 x-intercepts. And then we have the 3 repeated situation, which looks like this. So notice that we still have 3 real roots, all of them are repeated, which means that there's only 1 x-intercept that shows, and again notice that there are no imaginary zeros. Now, the only other situation that can happen is, of course, being that our imaginary roots always come in conjugate pairs, is that there are 2 imaginary roots. And if there are 2 imaginary roots and they are conjugates, then that means that the last root, or the third root, because this is a degree 3 polynomial, has to be a real one. And with that in mind then, we are only going to have one x-intercept. And what that looks like is going to look something like this. So we have a times it by x minus alpha times it by a quadratic, which is going to have a discriminant which is less than 0. Okay, so what we're going to have to take a look at further is how are we going to analyze what happens with a quartic polynomial, which is of course degree 4. And so I invite you to go ahead and take a look at what you think would happen based upon the discussion that we had for both the degree 1, degree 2, and degree 3 polynomials. And let's see if you can find out what that would look like here in terms of the function. How many real roots are possible, how many imaginary roots are possible, and how many x-intercepts are going to show up based upon all of those different possibilities for the quartic function. Okay, so we'll go ahead and take a look at that, and then we'll go ahead and take a look at some of the problems that appear in this particular section. See you next time. Bye-bye.